trying to figure out what the best way is for me to do this. I think I'm going to open up a new document because that makes it easier for me to type, because the whiteboard is sort of weirdly problematic. I can get this thing to actually show me the document. All right, so here is the example that I want to go through before we get around to going through the chapter 4 homework. All right, here is an equation. It would help if I put the right numbers in there. H2O, not H3O. H3O is something different. All right, so this is an unbalanced reaction. So first step is balance the reaction. So have a look at the fact that your sodiums do not match because my Na3P molecule already has 3 sodiums in it. I'm going to go ahead and go back here and put a 3 in front of my sodium in order to head me in the direction of making sure that I'm balancing this. So put a 3 there, okay? And that still doesn't quite fix everything, because that also means I have 3 oxygens in my sodium hydroxide molecule, and I don't appear to have enough oxygens on the left-hand side. So I'm going to go back and put a 3 in there. All right, so now I have a balanced equation. All right, so then here is the next set of data. So 150 grams of pH3, actually no, of sodium phosphide, Na3P, is mixed with 250 grams of water. And so what I want to find out is if the actual yield is 30 grams of my pH3 molecule, what is my percent yield? All right, so I need to figure out which one is limiting as my starting point. So if I take my 150 grams of sodium phosphide, and I am going to multiply by 1 over its molar mass. So 1 phosphorus and 3 hydrogens will give me, and I'm reading the wrong molecule. It's supposed to be 3 sodiums and 1 phosphorus, because it's 99.94 grams. All right. So that gives me 1.5 moles. All right. Then I've got 250 grams of water. Which is much lighter in weight as far as molar mass goes. So it's 18. And that will give me 13.89 moles. All right. Look at your balanced equation. Now, typically speaking, the one that you have the smaller number of moles in is usually the limiting. I do have to pay attention to the fact that there is a coefficient of 3 out in front of my water molecule. So even if I used up all of my 1.5 moles of sodium phosphide, I would still only need 4.5 moles of water. So yes, this one is my limiting reactant, because I am going to run out of that long before I run out of the water. So I'm going to use my 1.5 moles of sodium phosphide. And I have a relationship of 1:1. Yeah, actually, it's Courtney. I posted a wrong something or other and really kind of fouled this up. So I'm just doing this one example as an additional example while we wait to see who else shows up.
Okay, thank you.
All right, so 1 pH 3 per 1 sodium phosphide gives me the same number. I've still got 1.5 moles. I've just changed identity. Now it's 1.5 moles of pH 3. And then I need to multiply by its molar mass. So 33.99 grams per mole will give me 50.991 grams of my pH 3. Okay, and that is my theoretical yield. Basically, if everything had worked perfect, okay, I would have gotten a kind of large-ish amount, but it says my actual yield was only 30. So I'm going to do 30 divided by 50.991 and then multiply by 100, so it's a percentage. And that will give me 58.8%. So not a really great percent yield in comparison to what I could have gotten. But think about your steps here. So you've got 2 of essentially the first step in the roadmap. Your first step is all of this where you go from grams to moles. Okay. Then I go back and look at my ratio here of the fact that I need 3 waters for every 1 sodium phosphide. And I can determine then that this is limiting, because even if I have 3 times as much needed for the water, I still have way leftovers. Okay. If I need 4.5 moles and I've got 13, I have like 9 more moles than I actually need. This is also middle step information here of 1 pH 3 per 1 sodium phosphide. And your final step for the theoretical end of it is to multiply by your molar mass. And I actually kind of left out my little divide mark there. It's grams per mole. and then I look at my actual, divide by my theoretical, do the multiply by 100 as your final step, and that will give you 58.8%. So hopefully having an additional example also if for to go with notes and also to go with some other stuff that's in the textbook will be helpful. Questions about that one?
No, thank you.
Okay. Give me a second to pop open my email to see if anybody else sent me email about my dramatic stupidity. Yes. All right, and I have too many tabs open. Yeah, I screwed something up. Okay, so yeah, because one other person sent me email. I'm trying to unscramble all of this. All right, so I replied to that person's email. That was Heidi, who's in my Monday class, my Monday lab. Hopefully some other people will see the amended announcement. All right. Back to me trying to make sure I'm like clicking on the right file for this. All right. So this is the answer key for homework 4. I think I did actually post that correctly. I did that about half an hour ago. So let's talk about the balancing equations first. So when you look at the first one there, note that your nitrogens do not match. I have 2 nitrogens on the left-hand side. The only way I'm going to get this to work out, which will also solve my hydrogen problem, is to put a 2 out in front of my nitric acid molecule. So that one only required 1 correction in terms of coefficients. For the next one, look at your chlorines. They are the biggest hiccup in that particular equation because when you start out, you only have 2 chlorines, but you already have 4 in the carbon tetrachloride molecule, and there's this extra one that's part of your hydrochloric acid molecule. So in order to end up having 8 chlorines on each side, then you need a 4 for your Cl2, and you need a 4 for your HCl. All right, and then the last one is probably the messiest of the 3. Pay attention to the fact that your aluminum carbide molecule has 4 atoms of aluminum in it. So you can't have less than 4 on the right-hand side there. I started out by putting a 4 out in front of my aluminum hydroxide. That solves certain problems. It also gives me way more oxygens than I originally had present. I also had to deal with the fact that I have 3 carbons. And the 3 carbons then means I need a 3 out in front of my CH4 molecule. all of that gives me many more hydrogens and many more oxygens, with the final resolution to this being deciding how many water molecules you need. So the only way I can get all of this to match out is to actually use a double-digit coefficient. I do need 12 molecules of water in order to make that work. And I'm trying to figure out if my email sent. I think it's sent. Okay.
Sorry, ma'am, I have one question for number 3. I haven't, I had a different answer, but I thought it was okay, but I think, I don't know if you give me the point for it, but for number 3, I put 7 in front of H2O, 4 in front of AlOH3, and 3 in front of CH4.
The problem with only having 7 waters is that you actually need more oxygens, because look at where the OH is inside parentheses, and there's a 3 on the outside, so that's 3 molecule or 3 hydroxides right there.
Mm-hmm.
Then you have to multiply it times the big 4 that's out in front, because the 4 affects everything in the molecule. You actually end up with 12 atoms of oxygen. 7 will not give you enough to match on both sides.
So the 4. Now I thought like the O, because it's in the parentheses, it would be like 3 times O, which would give me like 3 oxygen plus the 4 in front of it. I didn't know you multiply it.
Yes.
I'm sorry.
Anything that is a coefficient multiplies by all of the atoms in the molecule.
All right, perfect.
If you were doing algebra and it was 6xyz, that means you have 6 x's, 6 y's, and 6 z's.
Yeah, I get it.
So the same idea kind of applies here.
All right.
I was looking to see if anybody else had actually tried to log in. Okay. All right, so let's talk about ions a little bit. Ions does mean that you are supposed to put the positive charges or the negative charges, but you also need to keep in mind that polyatomics do not fall apart in water. So your copper sulfate will only split in half. It will have +2 on the copper ion, but the sulfate, the SO4, all of that stays stuck together with the -2. And looking at the sodium acetate, okay, so again, this is one that just splits in half. You have a single positive sodium, and then the C2H3O2 is your acetate. And so all of that stays stuck together with a single negative charge. Now, your 2 potassiums that are at the front end of your potassium chromate molecule, they do not actually stay stuck to each other. You are not supposed to leave it as K sub 2. You need to actually pull the K out in front and assume that there are 2 separate ones. Let me go back to trying to use my whiteboard to kind of reinforce this. All right, so we've got a chromate which doesn't fall apart in water, which is kind of its own blob. And then you've got a potassium over here on this side. And you've got a potassium over here on this side. And yes, there are 2 Ks, they're just not stuck to each other. So here is where one of the breaks occurs, and then the other one is on the other side there. And so this is one of the reasons why you get 2 out in front of the K pluses. So 2 potassiums and 1 chromate that is a -2. All right, so for number 5, I did not ask you to balance it, but you did actually have to create neutral molecules in the solving of the answers. Yes, there are 2 chlorines available, but AgCl2 is not a neutral molecule. You cannot leave 2 chlorines together to try to stick them to your silver atom. You actually have to treat them as, use as many as you need. Okay, so silver chloride is your precipitate. This is the chloride rule. Most chlorides are soluble, but not silver, lead, or mercury. So here's the silver one. And then the second one, even if you swap them and you try to create K2SO4 or ammonium chloride, neither of those is going to be a precipitate. No precipitate happens because everything is soluble. All right. Now, number 6, I was kind of trying to lead you through the steps. So we look at the first one and it says, what are the ions? So basically, when you drop sodium carbonate into water, along with lead 2 nitrate, what pieces do you actually have available? So split off your 2 sodiums. So you have 2 positive sodium ions and 1 carbonate, because again, back to that concept of don't split your polyatomics. Your 1 atom of lead swims free, and then you have 2 nitrates. So I can swap. I can make things stick to what they did not come in with. They swap partners. So my sodium will attempt to stick to my nitrate, and my lead will attempt to stick to my carbonate. You must write it as 2 NaNO3s. Do not make them a duplicated subscript. Don't make it Na2NO32. The only molecule that is allowed for is mercury chloride. Everything else, you got to pull it out in front and make it a coefficient. Complete ionic means split everything but your precipitate. So lead carbonate is my precipitate based upon the 6th solubility rule, which says most carbonates are not soluble. Okay. I split all my pieces apart. I've got sodiums and carbonates and leads and nitrates. My right-hand side has 2 separate sodiums and nitrates. And that one last molecule that you leave assembled is my lead carbonate. And then the final step is get rid of all your spectators, get rid of your sodiums and your nitrates, and only deal with the ions that it took to make your precipitate. So remember, all precipitate net ionics kind of look the same in that something positive and something negative sticks together to give you a neutral molecule on the right-hand side. Number 7, then, I didn't go through the steps with the same level of explicitness. I gave you 2 things to combine and then kind of just gave you instructions to write a molecular and an ed. When you have your ammonium sulfide and your copper chloride, again, you got to pull your 2s out in front. You cannot make it NH4 to Cl2. It's got to be the big 2 out in front. That's also not a precipitate. You can use either rule. You can use the rule that says most ammoniums are soluble, or you can use the rule that says most chlorides are soluble. For both reasons, NH4Cl is not your precipitate. Cobalt sulfide is. And I skipped the complete ionic step because I was only looking for the net as the other half of this reaction, other part of this problem. So pulled it apart, cobalt +2, sulfide -2, product, one single molecule of cobalt sulfide. Now, I did not completely balance the left-hand side on the first one there for the acid-base reactions. I gave you HCl and I gave you calcium hydroxide, but because there are two OHs, you must have two molecules of hydrochloric acid. This will also give you two water molecules and a salt, the salt being calcium chloride. Now, the one below it, the second acid-base reaction, that one is a diprotic acid because it's got two H's there at the beginning of the sulfuric acid. Match it up with my strontium hydroxide, I still get two molecules of water. I just didn't need any additional coefficients on the left-hand side. And this time around, my salt molecule is strontium sulfate. So that kind of gets us up through acid-base stuff. And then we spent a little time on doing some gas generating, but not a lot of time. So I only gave you one example for that. And actually, I clicked on the wrong thing because I was trying to still monitor my email. Let me hit my share thing again. All right, so sodium bicarbonate, sodium HCO3, and some hydrochloric acid gives you three products. You get sodium chloride, you get water, and you get carbon dioxide as your gas. Some errors that I saw on the oxidation numbers, some people did not seem to understand that each and every element within a molecule must have an oxidation number. So the first one is Cl2. It's a pure element. Yeah, there's two atoms of it, but it's not stuck to any other elements. So I have 0 oxidation number. When I do MnO2, I need two answers to this problem because I have to have -2s for my oxygens. My manganese is +4. When you look at the permanganate ion, note there's a little negative sign beside it, meaning that all of my Mn charge doesn't quite cancel out all of my O's. I have one negative that never got canceled out. So this makes my manganese +7. Bicarbonate, hydrogen carbonate, as an ion, has 3 elements in it. So it must have 3 answers. Hydrogens are +1 because they're not stuck to a metal, so they're kind of normal. My oxygens also are relatively normal because they're not stuck to like a transition or an alkali metal. And then you have to figure out again, one negative doesn't get canceled out. One of them has to be left over, which means my carbon needs to be +4. for my xenon and my fluorine. So 6 fluorines, they're -1 each. Yes, xenon is often not part of a molecule at all because it's a noble gas. You can kind of coerce it. And in this case, you get a +6 for your xenon. All right, then on to some redox. I've got iron 3 oxide and carbon monoxide. We do some shuffling and we get some iron, elemental iron, and some carbon dioxide. So you have to think about what's happening to each of your elements. You've got 3 elements. You've got iron, you've got copper, you've got oxygen. So my iron, when it was in the molecule, started out life as +3. It then becomes 0, which means it got reduced. That makes it an oxidizing agent. The carbon went from being part of a CO molecule to being part of a CO2 molecule. So its oxidation number goes up. You started out as a +2 and it went up to a +4. That means it's oxidized, but it also then is a reducing agent. Oxygen technically did nothing. Okay, oxygen didn't lose any electrons and it didn't gain any electrons. The oxygen is actually kind of a spectator in the world of the redox reaction. So number 12 was another one where I was trying to kind of lead you along through some various steps of stoichiometry. We have a 5 fluorine, 2 ammonia set of reactants. We have 1 N2F4 and 6 hydrofluorics as our products. So I actually kind of started in the middle. What's your ratio? Find goes on top. Whatever you know or wish to cancel out / get rid of goes on the bottom. So I have a 2-to-5 ratio. And I kind of backed up kind of to the first step of stoichiometry. If I give you 25 grams of fluorine, how many moles is this? So 2 Fs is not quite 38 grams. Although if you use 38, it's not going to significantly change your ending answer. 25 divided by 37.96 gives me 0.659. And then I combined the two things. This is why it actually kind of tips you off. Use information from B along with the stuff you already found out from A to figure out how much ammonia you need. You need 2/5 as much. So multiply by 2, divide by 5 from your answer above. Then I swapped over to the product side. So if I know how many moles of fluorine I have, how much HF am I going to get? It does say moles, so that one does not ask you to convert it back to grams yet. That's the one below it. You have a 6/5 ratio. For E, now take the answer from D and multiply by, and I actually just suddenly realized that I'm missing a little hash mark here. It's supposed to be grams per mole for the 20, your molar mass there. And you get about 15.8 grams of HF. And then the last thing was, well, okay, there's actually a second product, which is the N2F4. How much of that do I get when I started out with the same 25 grams of fluorine? None of the steps in this problem ask you what's limiting. You are assuming that the fluorine information you are given is basically the controlling factor for all of the problem. So take your 0.659, multiply by 1/5, then molar mass of 104.02, and you get about 13.7 grams. Some of the errors I saw, some people flip-flop their ratios. They put the wrong thing on top. And a couple people, I think, also made errors in their molar mass. So keep an eye on your periodic table information when you are calculating molar mass. All right, number 13 is less lead you step by step. I gave you a reaction, it is balanced, and then I gave you a bunch of information and you have to figure out a few things about it. So if I've got 56.6 grams of potassium platinum chloride and 34.6 of my ammonia, how many grams of the big product are going to be produced? So I got to figure out which one I'm going to run out of. I did the same step or the same methodology twice. Once for the potassium platinum chloride, once again for the ammonia. Obviously, the molecule that has the platinum in it weighs a lot more in terms of molar mass, 415. I have a pretty small number of moles of that molecule. My ammonia, which only has a molar mass of 17, I've got more than 2 moles of it. So even though I need twice as much, because it's a 1-to-2 ratio, I'm going to run out of the potassium platinum chloride long before I run out of the NH3. And then I have a 1-to-1 ratio of both of the molecules that contain the platinum. Okay, it's one of each. And actually, I probably should have written a number 1 out in front here to make it a little more obvious. So 1-to-1 ratio there. Your mole amount doesn't change, but when I do the final step of, well, what if I had gotten 100% yield, which is my theoretical yield, I would have gotten 40.8. I got a little less than I was expecting. Multiply your 95%, 0.95, times your theoretical to give you 38.76 as your ending answer there. And some people I know did not carry 3 decimal places. You might have ended up with a slightly different number if you only had 2 decimal places in your moles. I tried to make sure I paid attention to that when I was doing grading stuff. All right. Figuring out what's limiting. None of these required you to calculate anything about the product. We were only comparing pairs of limiting pairs of reactions to see which one is limiting. So when you look at the first one, I've got aluminum and I've got chlorine. If I used up all my aluminum and I have a 3-to-2 ratio, that tells me that I would need 2.1 of the chlorine to go with it, and I'm in luck because that's less than what I have available. I have more than 5 moles available. I only need 2 of them. When I do the next one, however, if I pick the smaller number, 3.4 moles of oxygen, this one's a 2-to-1 ratio, I would actually need 6.8 moles of hydrogen. So my guess was wrong. Therefore, it's always an either or thing. All the ones that we're looking at this semester only have 2 reactants. So if it's not one, it has to be the other one. So it wasn't the oxygen, it had to be the hydrogen. For the last one there, I have quite a bit less P4O10, but I have a 6-to-1 ratio. If I use up all my P4O10, I need more, almost 3 moles of water. I've only got 1.5. So it can't be the P4O10, it has to be the water that's limiting. And then the last one is just kind of a straight through 3 steps. The key to this one is I did not give you a balanced reaction. So you must balance your reaction, otherwise the middle step of the problem won't work. So 6 sodiums and 1 molecule of N2 gives you 2 molecules of Na3N. So first step, from grams to moles, divided by 22.99. I got 0.435 moles. Then here's where your balanced reaction comes into play. 2-to-6 ratio. I have 2 product molecules for every 6 sodium atoms. For the last step then, because it does say how many grams, I need to use a molar mass of NaN3, which is just shy of 83. And I get about 12 grams. That one, this problem, you did not need to determine which one was limiting. You just start with the information that's given. Questions about Chapter 4 homework? All right, before we get into gas laws and all, let me talk about your upcoming test, because remember the test is going to be, unfortunately, over your holiday weekend. So I'll talk about this more on Thursday too, but the test is 2 chapters, okay, chapters 3 and 4. So we've got things like empirical and molecular and percent by mass and other related things from that chapter as about half the test. And then the other half of the test, probably actually a little bit more like 60% of the test, because it's a little bit lopsided. Chapter 4 is longer than chapter 3, is similar to the homework set here. We've got balancing stuff. We've got precipitation reactions, which means you need to make sure you are reading the solubility rules. We've got a little bit of gas generating. I'm probably only going to give you like 1 question about the gas generating. We didn't spend a whole lot of time about that. And you do see it in lab because it was in last week's lab for metathesis, but you only get a little bit of information about it. So not too much about the gas generatings. Little acid-base stuff, because that actually comes back again for this week's lab, and it also carries over again into next week's lab. Redox, which means you need to be able to do oxidation numbers, but then you also need to be able to tell me what got oxidized and what got reduced. Remember, there's a minimum of 1 each. Might have more, but minimum of 1 each. With the last segment of the chapter being the stoichiometry, which, okay, I will confess, and I've been doing this a really long time, stoichiometry is generally speaking the thing that the most people hate the most, okay, because it's a process. When you're doing, the thing that comes to mind since I did this recently with my daughter, dividing polynomials is like a thing you do in algebra that I mean, I don't have any problems with it. I just find it annoying. But it is something that algebra students often have a lot of problems with. It's kind of how stoichiometry ends up being. It's this, you do this, and then you do this, and then you do this. So it ends up being a process-oriented set of calculations. So kind of keep that in mind as you're thinking about things you might want to ask me on Thursday, because like I said, I'm going to talk some more about test information on Thursday, because that will be the last class day before the test. So let's take about a 10-minute break, and then we will come back and do a little more of gas law stuff. And I'm going to check my email again and see if anybody else is lost and due to my great brain fart. I'm going to push pause here. I also put 2 more YouTube links up for some previously recorded stuff, so you can go back and check them later if you want. So before I get back into actually chemistry things, so we'll see if I can stand this up so you can see it without it falling out of the pie pan. Okay, the reason it's in a pie pan is because it got baked. If any of you are Animal Crossing fans, this is something my daughter just finished creating. It's made out of Sculpey. I believe her name is Francine. She's one of the Animal Crossing characters. So I thought she had done a really good job on it, so I thought I would show her off. All right, so before we go on to some of the gas law stuff, which we probably won't get all the way through today, questions about stoichiometry, chapter 3, this week's labs, because remember, technically we're on this cycle, so the limiting reactant lab and metathesis are kind of overlapping with the titration lab that we are doing this week. All right, let me find my file, hopefully. All right, we are in the middle of chapter 9 because this is the one chapter that is not in order in terms of how we are progressing through the textbook. The last thing we were talking about Thursday was the ideal gas law, where we spent a little time talking about the fact that this particular equation is unbelievably picky. It has very specific units that have to be used in order to make this equation work out the way it's supposed to. We had pressure, which is in atmospheres for this semester. If you go on to take 112, there is a variation on this particular equation that makes use of a different unit, makes use of the millimeters of mercury unit. Your volume must be in liters. All of this matches up with your universal gas constant, which is 0.0821. If you're, like I said, looking for examples that are not in your textbook or other websites, you also might see an unrounded version of this, which is 0.08206. So this is the slightly rounded version of that. And everything we do in this chapter in terms of temperature has to be done in kelvins. All right, so on to the next equation. This one is known as the combined gas law. What it does is it kind of smushes three laws together. Boyle's had P's and V's side by side. Charles had volumes and temperatures as a top and bottom of your fractions. So if you kind of mash it all together, you get this combined version, which has one set of variables, which all have ones, so P1, V1, T1 on the left-hand side, and all sub twos on the right-hand side. So one of the things that this does for you is it eliminates the having to not change one of your items. Because when we talked about Boyle's law, we said we are assuming we're not changing the temperature when you're comparing your pressures and your volumes. Or when we looked at Charles' law, we said, okay, since we're dealing with volumes and temperatures, we're going to assume that your pressure is not changing. This particular equation allows you to change all three variables independent of each other. So I started out with a sample of gas, and it has 7 atmospheres of pressure, a volume of 6 liters, and a temperature of 17 Celsius. Note, I'm going to have to change my unit for my temperature there. I've got 48 Celsius as my new temperature with a new pressure of 1.4 atmospheres. So the only thing that I am missing is basically V2. I'm actually going to squish this over and make it a little bit more lined up here. When I put everything in, make sure you are converting your Celsius temperatures over to Kelvins. So 290 is 17 Celsius because it's 17 plus 273. And then 48 plus 273 will give you 321. And I did my cross multiply method on this. 0.7 and 6 multiplied together give you 4.2. And then next step down, I do my cross multiply. So I've got 4.2 and 321. And then 790 and 1.4 and V, or you could go ahead and carry the subscript with it and call it V2. Finish your multiplication on the left-hand side, 1348.2, and 290.1 times 0.1 or 1.4 will give you 406. Do your division as your final little algebraic rearrange, and you will get 3.32 liters. Now, one of the downsides, sort of, to the combined gas law is we talked about having a level of predictability when we were looking at the other 3 laws. So let me swap back over to my whiteboard for a second. So we talked about if you had pressures and volumes, you could make these kind of guesstimates of if your pressure is going down, your volume is going to increase. We could also flip-flop that and do if pressure is increasing, then your volume would have to decrease, okay? But you're only changing one thing at a time. When we looked at volume and temperature, we could make a prediction that said, because this is a direct relationship, we could say that when volume increases, we are assuming this is because temperature increases. Or when volume decreases, we can assume the temperature decreases. We also had Gay-Lussac's law, which was pressure and temperature. That one's also a direct relationship. P is increasing when your temperature increases, or the other flip of pressure decreases when temperature decreases. Like I said, the kind of the downside to the combined gas law is there's not the same level of somewhat predictability. So my pressure went up 0.7 to 1.4, but I also increased my temperature. I can maybe guesstimate that obviously I'm going to have some kind of a change in my volume, but I can't make a flat out prediction. Is it going to go up or is it go down? It ends up being all about the math. You actually just have to flat out do the number crunching, and hopefully make sure that you have no math errors in terms of finding the answers for that. Stoichiometry doesn't go away. We talked about the third legs of the stoichiometry map because somewhat traditionally, we can go from grams to moles of something else and back to grams. But we also said sometimes it involves Avogadro's number, 6.02 times 10 to the 23rd, but it also can involve gases. So STP is standard temperature and pressure, which doesn't quite exactly make as much sense as you think it should because, okay, the pressure looks pretty normal. We're at 1 atmosphere. We live at 1 atmosphere because we're in tidewater. But instead of being at kind of an average room temperature, it's actually at 0 Celsius. So it's colder than you would probably expect in terms of giving this as criteria. We can, however, say that any mole or a mole of any gas, presuming it's behaving as close to ideal as we're going to get, you will get 22.4 liters. One of the labs that is coming up a couple of weeks from now asks you to calculate molar volume of a non-ideal gas. So we're going to generate some carbon dioxide using a calcium carbonate sample and some hydrochloric acid. This is a reaction we've seen before, but we are going to capture the bubbles of the gas in an upside down graduated cylinder and then use that as information to calculate molar volume, because carbon dioxide is not an ideal gas. It sticks together a little more than a true ideal gas actually should. You can also use this idea as kind of a ratio, okay? If 1 mole gives you 22.4, as long as you know something is at STP, you can do it 2 different ways. I set it up as a proportion. You could actually do it in terms of a conversion factor. Either way, you should get the same answer. If 1 mole is 22.4, 0.39 is something. Well, okay, it's less than 1 mole. So I have a level of predictability again. I am expecting a number less than 22.4. Finish out my math there, do 22.4 times 0.39, and that will give me 8.736 liters. All right, back to stoichiometry. Mercuric oxide, HGO. If you heat it, it will decompose, fall apart, into some actual liquid mercury, and it liberates some oxygen gas along the way. I want to find out how much oxygen, and this means I'm in liters for my answer, when I do this with 25 grams of mercuric oxide. And I have a little bit of things that are kind of squunched out of alignment here. So 25 grams, mercuric oxide is kind of heavy. We have a molar mass of 216.59. So I have a little over a tenth of a mole, 0.1154. This is not a strictly 1-to-1 ratio here. This is a 1-to-2 ratio. We're looking for oxygen, so it needs to go on the top. We're using up HGO, so it goes on the bottom, each with its accompanying coefficients, 1 and 2. I have 0.0577 moles of oxygen, and then I can do that final step that makes use of the 22.4 liter number. I have much less than 1 mole. I do my multiplication. I get 1.29 liters of oxygen gas. Now, sometimes the information starts out more complicated. I have nitrogen gas and hydrogen gas making ammonia. Also, I don't have 1-to-1 anything here. I've got 1, 3, and 2. The other information that I'm given is not in grams and it's not in moles. It's in information that uses the ideal gas law. Okay, so we'll even kind of go back here and put this in so you can see it. So use PV equals nRT. Actually, my T should technically be capitalized in order to figure this out. So 4 liters, 1.2 atmospheres, 25 Celsius. 7.9 liters, 0.9 atmospheres, and a little warmer at 30 Celsius. And I probably actually should have said how much is produced at STP, because I am going to make use of that idea. All right. P, 1.2 atmospheres. V, 4.0 liters. And I don't know. 0.0821, that's my R value that doesn't change. And 298 Kelvin, because that's my 25 Celsius. Crunch my way through this. I end up with 4.8 on the left-hand side and 24.4 on the right-hand side. Finish your division. And I end up with 0.196 moles of nitrogen. I need to do kind of the same thing for my hydrogen, but my numbers are different. I've got pressure of 0.9 atmospheres. Have bigger volume this time. I've got 7.9 liters. 0.0821 doesn't change. My temperature is a little bit different. It's 303. All of that crunches down to 0.286 moles. But this wasn't 1-to-1. All the way back up here to my equation. This was a 1-to-3 ratio over on the reactant side. I need to figure out which one I'm going to run out of. So I put my guess in. So I picked the smaller one because that's usually the typical guess. 0.196. Use my 3-to-1 ratio. My guess is wrong. I actually need 0.588 if I were going to use up all the nitrogen. I don't have that much. I've only got like 0.28. So the hydrogen is the limiting one. And then this is my starting point for the next step. I'm using a different ratio here, okay? My ratio is 2-to-3. I'm making NH3 molecules and using up H2s. So that's where my 2-to-3 ratio came in. I can make 0.191 moles of ammonia. And then my final step is multiplying by 22.4, and I get 4.28 liters of ammonia gas. And actually, I'm like looking at this and scratching my head. Apparently, I retyped one line that I don't know. I don't know why I retyped it. That was kind of odd. Yeah, that's not actually supposed to be there. All right, so stoichiometry with gases. We can twist and convolute and manipulate the ideal gas law and use it to find densities. If you want to go back and look at their derivation, it is in the textbook. I'm not going to go through how you derive the equation. Take it on faith. We have molar mass, and this is also something that I kind of can't get my computer to really do. This segment here, okay, is actually under a square root sign. I'm not really sure how to coerce Microsoft Word to make it look the way it's supposed to. Let me go back over here to my whiteboard. All right, so M for your molar mass. Okay, big square root symbol, okay, with everything underneath it here. So we've got a scenario where you have lowercase d, capital R, and capital T. And then over top of P. Okay, so this is kind of how the math works. So let me go back over here to my example. All right. Uranium 6 fluoride. Okay, it's actually a solid at room temperature. However, you don't have to heat it up too very high in order to actually get it to boil. So we want to find out the density at 60 Celsius and 745 torr. All right, so some things that, okay, you need to keep in mind here. So the 60 Celsius, this kind of follows along the lines that, all gas equations need to be in Kelvin for temperatures. But this equation also bears some similarities to your ideal gas one. Is this equation needs your pressure, I spelled pressure correctly, to be in atmospheres, because otherwise I couldn't use the 0.0821 as my R value. So my molar mass is 344.96. Actually, I just realized I read too many lines down there. 238 plus 6 times 16, 6 times 19 gives you 352. Okay, put that in. We have density, which is our unknown. We have 0.0821, which is our R value. We have 333 is our Kelvin temperature, and our pressure is slightly under 1 atmosphere. Crunch all of that, and okay, I'm mixing two equations. Let me double check this. I think I actually put a square root somewhere where I don't need to put it. Give me a second. I'm jumping ahead. Yeah, actually, I did screw that up. There is no square root in there. I'm jumping ahead to the last equation of the chapter. It's been one of those days. So yeah, this is actually written incorrectly here. Molar mass is dr T over P, because I just suddenly realized 344 divided by 27 is actually about 12. So there's the ending answer. There is no square root in there. I'm combining it with Graham's law of effusion, which does have a square root in it, which is actually further closer to the end of the chapter here. So let me do, I'm going to get rid of this. Let's do one kind of from scratch then. So let's say I have a density, and this is for a gas, of 4.6 grams per liter. And my R value doesn't change. My R value is 0.0821. We're going to say the temperature of this gas is 45 Celsius. And our pressure is 120, 450 pascals. We want to find mass. And it would help if I spelled find correctly. All right, so we have density 4.6 times 0.0821, but I need to convert my T value. So my T value is going to end up being 45 Celsius plus 273. So that's 200 or 318 Kelvin. And then I draw this. We'll put a line here and we'll put pressure on the bottom. But I'm going to do pressure over here. All right, so 120, 450 pascals times 1 atmosphere over 101,325. And that will give me, and I can't do that in my head, so let's see, 12450 divided by 101,325 gives me 1.19 atmospheres. So I'm going to put 1.19 on the bottom there. And then I need to crunch all my data. So I'm going to do 4.6 times 0.0821 times 318. And that will give me 120.09 divided by 1.19. And that gives me a molar mass of about 100.9. Okay, that would end up being in grams per mole for that. Yeah, to give you at least a decent example, since I erroneously skipped ahead in my brain and tried to put a square root in this. All right, questions about Chapter 4 homework or this middle section of the gas laws? We will finish gas laws on Thursday, but I will probably not make the homework due until Tuesday night, because the test will run through Monday at midnight, and then that will give you an extra night to finish up homework if you need the extra time. Also, that will give you a kind of not quite so much overlap between necessity of taking the test over the weekend and also some necessity of working on homework too. We're kind of stuck. 10 weeks is all we get this summer. So not quite to the end of chapter 9 yet, but we're getting there. Test coming this weekend. Questions? I will see some of you tomorrow night in lab.
Okay, thank you.
Thank you.